All right, sections 3.2 through 3.5 are going to each one encounter one of our four basic operations. Today's addition. The next one, 3.3, is going to be subtraction, which means 3.4 is going to be multiplication, and 3.5 is division. Okay, so we're working on one operation, and all of them we're working on these operations within the whole number system. This whole chapter is about whole numbers, so no fractions, no decimals, no negatives, nothing like that, just whole numbers. So to start with, we need a definition of what we mean by addition. So you might remember back in chapter 2, we talked about sets. Well, this is the set definition for addition. So let A and B be two disjoint, right? That means they do not overlap, disjoint finite sets. If the number of items in set A is lowercase a, and the number of items in set B is lowercase b, then adding the number together, A plus B, is the same as finding the union of the sets and counting the union. All right, so we take all of my people in my household, we take all of the people in my sister's household, those are disjoint sets because nobody's living in both households. We find the union through all the people together. If we count that, that's the same thing as adding the numbers of people together. It's the same step. The numbers A and B have a name. They're called add-ins. They're the numbers you are adding together, and A plus B is called the sum. Contrary to what one of my children says, this is not called plussing. This is called addition. Yes, and the other one's not called minusing or timesing. None of those things are actually proper math language. This is addition. All right, so we're going to start with an example of why it is necessary that our sets are disjoint to actually make this definition work. So in order to do that, what that means we're going to do is we're going to create sets that are not disjoint and show that it fails, that this definition fails to actually make sense. So we can do that with lots of things. The easiest thing to probably do it with is just a few numbers. And we want our numbers that are in set A and our numbers that are in set B to overlap to some extent. So we're going to let A be the numbers 1 through 4. So 1, 2, 3, and 4. And I will let B be the numbers 3 through 7. Okay, they're not disjoint, right? They overlap. They overlap specifically in the numbers 3 and 4. Agreed? Okay. So if I were to count the number of items in set A, how many items are in set A? 4. And if I were to count the number of items in set B, I would get 5. And if I were to add these together, I would get 9. Okay? But if instead I find a union B, remember unions mean I get all the numbers, but I don't write anything twice. So I would have the numbers 1 through what?
7.
Yeah. And there's nothing super special about this example. Any example where they have overlapping values is going to work on this. Sometimes our examples need to be really specific to make something work. This is not one of those. They just have to overlap and it's going to fail. And the number of items that you just wrote down is actually 7 items, right? And what you notice is that these two numbers are not the same. And that's what that definition says. It says that the numbers added together, A plus B, should be the number of items in the union, and we see that it fails. And the reason that it fails is because they weren't disjoint. There was an overlap, right? So this would be sort of like imagining that you had maybe like a divorced situation, right, where the child goes back and forth. You wouldn't count the child twice, right? The child does, in fact, live in both households, but they would not be double counted. All right. There are, I think it's 3 models. No, they eliminated one. That's right. I forgot. There are 2 models that they use for addition. So whenever our book calls something models, it means that there's some concrete way that the problems, generally, that the problems themselves are worded differently based on the model that you're using. So the first model is called a set model. And the second model is called the number line model. So a set model is typically used for whole objects, something where we only count a whole object, right? For example, crayons. It doesn't matter if the crayon's brand new or if it's half used. When you talk about a crayon, you talk about it as though the object were a whole object. And that's just how we describe crayons, right? That's just our context. So this is an example of a set model problem. Liz has 3 blue crayons and 2 red crayons. If she combines all the crayons, how many crayons does she have? And so when you're working with a child, right, preschool, pre-K, maybe kindergarten, depending on what they've been exposed to or whatever, like you'd literally get out crayons for this problem, right? And you'd have them go 1, 2, they count them to see how that works. So I remember when my 8-year-old, who's over here on the floor right now, was in kindergarten. It was kindergarten. And I remember them doing addition and subtraction and thinking like, they're doing addition and subtraction. That feels like it should not be a kindergarten topic. But they were doing it from a concrete model perspective. So it really was a kindergarten topic. She wasn't memorizing flashcards. She wasn't doing that sort of thing. She was counting. That's what she was doing. So when we're looking at this and we're drawing these sorts of pictures, you want to imagine drawing these crayons. So we started out with 3 blue crayons. And it doesn't matter that they're all the same length, although if you wish to make them so you can. So here's my 3 blue crayons. And then it says I have 2 red crayons. And I physically would count the crayons. And I'd put them all together. And combined all together, I would find that I have 5 crayons. All right? Concrete model. Not everything, however, even if they are whole numbers, are thought of as whole objects all the time. So we do have another model called the number line or the measurement model. Those words are used interchangeably. And it's typically used for objects that can be partitioned. Okay, we're still working with whole numbers here. But while we don't usually say half a crayon, unless they actually broke the crayon in half, that might be a situation where you might. That's not usually what we say when we think about crayons. We think about some objects very much that way. For example, Joe has 4 feet of wood. Right? It's not counting a piece of wood, it's counting how long the wood is. It doesn't have to be a whole number, but we're working with whole numbers. But we're not counting objects, we're counting some sort of a measurement about the object, in this case length. So Joe has 4 feet of wood and 3 feet of aluminum. How many feet of building material does Joe have? So in some sense, we're sort of measuring this, and you see us draw a number line to do so. So we're going to draw out a number line. And we have, the number line starting here at 0. And here is our 4. I'm marking it here. I'm not sure that I'm going to get these quite exact, but here's another 4. Right, that's not what I meant to do. He has 4 feet of wood. That's what I meant to do. 1 is what I meant to do. 1. Okay, and then here's my 2. There we go. Here's my 3. And here's my 4. So the first one was wood, so I'll use brown. And we have a 4-foot long piece of wood, right? And we sort of lay them end to end. And then we have a 3-foot long piece of aluminum. So we'll mark out a few more feet on here. So we have 1, 2, and 3 more. So my aluminum would go here at the end, make aluminum silver. And if I count on from 4, I have 5, and then 6, and then 7. And the length of these, building materials placed end to end would be 7 feet. So we have 2 objects we're counting, but this is the length that we're talking about of those objects, even though we're still working with whole numbers. All right. The idea of less than shows up in this section, and there's a specific definition, the way that it's phrased, but we can alter the definition as well for equally good definitions. So the one that they give us as sort of their given says for any whole numbers, A and B, A is less than B, written with the symbol, less than, if and only if there exists a natural number K such that A plus K is equal to B. So just with some real quick numbers, what it's saying is that the reason that 4 is less than 6 is because I have the ability to add something into the 4, a positive whole number, right, that's actually going to make this statement equal. And of course, that number here would be the number 2. So if I have one number that's smaller than another, I always have the ability to add something to it to make them equal. Now, like I said, this isn't the only definition of less than, all right? We can also use the definition that involves subtraction. This definition involves addition. So when we're working with this question, number 2, which is saying do the same thing but use subtraction instead of addition, almost everything that's written here is going to be the same. It's going to be the same right up until the point of the equation that says a plus k is equal to b at the end. So this is a great problem because all you're going to do is copy what was already written. Okay, so that's how we're going to start. It says give the definition of of addition using subtraction. So we're going to write down the same thing we had before for any whole numbers a and b. A is less than b. Written same way as before, a less than b. If and only if there exists a natural number, remember natural numbers are the whole numbers but not 0, a natural number k such that, and this is where it's different, the very last part. Instead of it saying a plus k is equal to b, what could it say involving subtraction using those same letters? Yeah, so I'll keep the order the same, so a is equal to b minus k. So instead of adding k to the a, I could simply subtract the k from the b. And this is equally good in terms of a definition of addition as the first one. All right, I think we'll probably stop there. We'll pick up with the whole number properties of addition next time and continue from there.